This is a review video on dynamics and forces. And in this video, I will briefly go through some core concept, like a few forces that we introduced in class, and also the connection between the force and the motion. And later on, I will focus on 3 problems to show you like some problem-solving strategies when you are dealing with a problem with, like involving the forces and the accelerations. All right, so let's see. Newton's first law. Newton's law pretty much tell you why things move in that way. So first law tell you that if there's no net force, then every object, they don't want to change. They either, if they were at rest, then they will stay at rest. If they were moving, then they will just continue moving at the same velocity. Okay, so that's the first law. And the second law is saying, when I have some non-zero net force, then that net force will drive the object to, will accelerate this object. Okay, so this is Newton's second law. And Newton's third law is saying action and reaction force. So this one is a little bit subtle. All right, so for example, if I have someone push another one, so for example, a dad is like pushing his baby. So this dad will push this baby, and this baby will be like push over, right? Like push over. Now the question is, the dad will exert a force on baby, and the baby will exert a force back. Daddy to baby, and compared to baby to daddy. These forces, although it seems like really weird, but these two forces are exactly the same. Just different direction, because one is exerted on baby, one is exerting on dad. All right. Okay. So so try to convince yourself this is true. And one way I find sort of convince me is, for example, if you clap, or like if you hit your baby really, really hard, then your baby will feel like he's hurt, like he's hurting a lot. But also your hand also feel like it's hurting. So there are some force exerting on your hand and some force exerted on your baby. So, and this force are exactly the same, are equal, but in the opposite direction. So when you clap, both of your hand hurts. All right, so this is the relation, and there are some forces that we talk about in the class, such as normal force. So normal force is the force coming from, which is normal to the surface, right? And gravitational force, there's really no formula or definition for this normal force, besides, we know its direction is perpendicular to the surface. Gravitational force is mg if you are around at the surface of the earth. Tension is just a tension of a string. We don't really have like a definition or which can help you to calculate the value for tension. It's sort of dependent on the situation. For the drag force, so the drag force, this force is coming from the fluid. So say when you are flying or when you are swimming in the water, you will feel your water is pushing against you. That is the drag force. And that drag force has something related to the water, right? So it related to the fluid, the coefficient of the fluid, related to the density of that fluid. If your water is very, very dense, then you will also feel more resistance, more drag. Also depend on your frontal, the surface area, and depend on your speed. So if you're not moving, so for example, if you stay in the water, you're not moving, then you won't feel any drag force. But once you start moving, when you're swimming faster and faster, you'll feel that water is the dragging for the water is pushing against you more and more. So that's why you can see the drag force depend on the relationship of object force and V is like in this way. All right, now it comes to the friction force. So friction force, it's also kind of subtle, because friction force, if the object is not moving, we will have static friction force. So for example, if an object here, it is not moving, but if it's totally completely not moving, then there's no force. But if you push it a little bit, but the push is not big enough to make it move, it still has some friction force, and that friction force is called static friction. So you can keep putting on a lot of push force until a moment. After a moment, this guy will just start moving. So that moment we call maximum static. And once it starts moving, we call it kinetic friction. This one is pretty much dependent on how much push force I exert on, so the friction will just be generated to go cancel out my push force. But for the maximum static force, friction force, and kinetic friction force, this two depends on, it actually can be determined by the surface and the normal force of this guy. So these two are the friction coefficient, and these two are normal force. Okay, so for example, this guy now has a friction. If I make it heavier, so that the normal force is greater, it will be harder to push it because the friction is like larger. All right, so the normal force, the larger normal force is, the friction will be larger. That's friction force, and the next is spring force. So if you have a spring like this, there's no spring force if it's at its equilibrium position. But if I stretch it out, makes it like this, I stretch out this amount, like then I will feel like this spring wanna be restored, right? It wants to come back to its original position. So this spring will exert a spring force on this object. And that depends on the spring itself, and also depend on how much you stretch it. If you don't stretch it, then there's no spring force. But if you stretch it, the more you stretch it, the more spring force you will experience. So that's why this is looks like this. All right. In this example, I will show you an example of a dynamic problem which involves normal force and gravitational force. Consider a bug on a grasshopper in an elevator with acceleration a equals to 2 going up, and find all forces acting on the bug and the grasshopper. All right, so we want to find all the forces. If you're not sure what to do, the best way to start this problem is to draw a free body diagram, because that will help you to organize your thought. So the free body diagram of the bug looks like this. The bug has a gravitational force. It has a normal force, because you can see the bug is standing on the grasshopper, right? So there's a contact surface. So which means the grasshopper is pushing, like supporting this grasshopper, supporting this bug. So we have a normal force from grasshopper to the bug. All right, now let's come back to the grasshopper. For the grasshopper, we have the gravitational force of the grasshopper. We have the normal force from the ground to the grasshopper. We have the normal force from the bug to grasshopper. All right. Are this all? Like, do we miss any forces? Let's do another check. So you can run through all the forces that we introduced, and also use your intuition, like your observation, see whether you can find more forces. All right, there's a surface. As long as there's a surface, there's a normal force. So this is bug to grasshopper, come over here. All right, this is ground to grasshopper, come over. All right, it's all clean. And gravitational force is a long distance, it's always there. Okay, once we're done with this, we can apply the Newton's law. So for example, before we apply that, let's see how much we can get out of definition. Remember we said that there are two approaches to find, just in general, there are two, like in problem solving method, there are two ways to approach a problem. So first, you can ask, what's the definition what's the definition of your goal? For example, if I want to find A, and I know A is delta V over delta T, then I just need to find delta V delta T, right? So that's like the approach of a definition. So all of these are kind of like definition. It's like pretty much already determined by the materials itself. Another way that we can approach a problem is we can do it from the relationship. Sometimes the definition is not very helpful, especially for normal force, tension. They're not very helpful. And so in that case, we can come to the relation. Relation can usually tell us some story. So now here I want to show you how to do it in two different ways. Okay. So first, I'm gonna do it in the definition way. What is normal force? Definition of normal force is the force normal to, perpendicular to the surface, which is not really helpful for me here. I mean, it's helpful to help me to draw the direction, but not in the value. How about this? Gravitational force. Fg equals to mg. So this is mg, m bug g. So which is 1 gram, so it would be Newton. All right, so this one check. How about here? Again, we don't know about normal force because its definition is not telling us anything about the value. Again, we don't know about the value of normal force, but we do know this. This is mg. All right, so check. Now we want to find all forces, right? These are all our forces. We already identified 2 of them. We need to identify 3 more. All right. So now I'm gonna show you, like I'm using another color. Now I have tried out all of my definition. I can only do this 2. Let me try the relation one. So here, let me use the relation. I know F net equals to MA. M bug A. So what's the net force? The net force, we only need to care about y direction in this case. The net force is the sum of all forces. So in the y direction, the sum of all these forces will have normal force, which is going upward. We also have this downward, the gravitational force, which is downward, so I put negative sign. So this is the net force. Equals to MA. M is M. And what's the acceleration here? It's 2. Acceleration of this guy is, because it's in the elevator, so its acceleration is also, the A is 2. Okay, so let me start to put in all the number and information I have. So this guy is this. This one is, so the F. All right, so this is the force the normal force from grasshopper to the bug. Okay, check. We know there's a very intimate relationship between these two forces. This is normal force, grasshopper to the bug. This is also normal force, bug to grasshopper. So these two, they are action and reaction pairs. So which means they have the same value. If this one is 0.012, then this one must be 0.012 as well. So this is like we sort of get this for free. Okay, this is our last object. How do we figure this out? Again, we are done with all the definitions, so let's come and use a relation. So in the relation F net, F equals to ma. So what's the net force in the y direction? The net force is, this one is positive, these two are negative. So I'm gonna just put in a number for now, minus this one, equals to ma. And the m of the grasshopper, we know it's 10 gram, and the a is 2. All right, so now let's put them together. All right, so here we're 0.112 Newton, 114. All right, so this is our last one. All right, now we have done all the job. We find all the forces acting on bug and the grasshopper, including their directions and their magnitude. So you see, like the logic is actually pretty straightforward. When we see a problem, if you're not sure how to analyze it, but it's involving with the forces, first step is to draw the free body diagram. Carefully draw the free body diagram, label them well. Once you label them well, like you can start it to, based on what's the questions, you can try to solve the questions by either definitions, or you can try to solve the questions from the relation, which is F equals to ma. And this is the logic of that. And later on, you will see more, you will see two other examples. We are sort of following the same logic, but just different forces. So please practice on this. This will definitely, once you master this logic, you'll feel more comfortable about it. This is another example of a force problem. Here you can see some tension force, spring force, and gravitational force. All right, so let's read this problem together. The spring is stretched by delta x, and the spring constant is k. So how do you express delta x in terms of k, m1, m2, and g? All right, so delta x means like how much is, by how much is this spring stretched? Okay. So this delta x is directly related to the spring force, and it's related to spring force in this way. All right, and so let's see, we want to express delta x, so let's just like move this over, so we get this. All right, so now we have k, but we don't have spring force, right? This is not in terms of this, all of these variables. All right, so how do we find spring force? Here we just use the information of, this is a definition of spring force. So it seems like we have already done with definition. We can go ahead and see what the relationship between F and A, to see whether that can give us some more information. All right, so our next goal is trying to find out this, and the way I'm going to find this out is to try to analyze F equals to ma, and there are two objects. To analyze F equals to ma, it is always good to start with free body diagram. Say if I want to do the free body diagram for the first object, I will get tension pulling this way, spring force, which will try to resist the change. All right, and I also have normal force and the gravitational force. All right, so let's see. Now this guy is not moving. So if we want to use use the relation F equals to ma, we can see that in this direction it's not moving, but we don't really care because we want to find spring force. Spring force, you will find spring force in this direction. So now let's see what's happening here. In this direction, the net force is T minus spring force equals to ma. But in this case, it's not moving, so A is 0. So we get spring force is T. So we know what is spring force. Spring force is tension. But hey, hold on, we still have no idea what is T. It's not in terms of all of these numbers. So we need more information. All right. So I think so if you think about this carefully, you will probably figure out that T will also appear on this particle. On this object in this direction. So let me give it a try. This is a mass 2, M2. So this object has a tension, which is the same tension as this one. They have the same value, and the gravitational force, which is mg. All right, so now again, let me analyze the F equals to ma. All right, in this direction, the net force is T minus Fg2. On this end, since it's not moving, so we know the acceleration is 0. All right, so now here we get T equals to Fg2, and Fg2 is nothing but m2g. So now we can plug this back to find out this guy. Spring force is tension. Tension is m2g. So spring force is m2g. Now let's put this back. So we know spring force is m2g delta x. All right, so now you may find that this is a little bit weird to have a negative because we know that this is positive, because we know this should be positive, like it's a change in positive. So so this should be something look like this, and this negative is coming from here. Because in this case, we know spring force should be negative, but just to simplify the calculation process, like we just sort of assume we separate the direction and the magnitude. So here we just go ahead and calculate the magnitude, and then we'll put in the direction later, like when you write the answer. Because I just find it easier to analyze it this way, to separate the magnitude and the direction. So direction, I would just put negative or positive. But for the value, for the magnitude, I would just put it as symbol. And in the end, when you write the solutions, and when you write your answer, you can just use your intuition to judge, to see whether it should be positive or negative. Okay. This is an example of a friction force. Okay. So in this example, I want to walk you through the static force, maximum static force, and kinetic friction force. All right. So again, the similar problem, the force is pushing the block against the wall. The friction coefficient is this one. So what's the friction force if the mass is 0.5 kilogram? All right. So now let's see. Let's draw a free body diagram on the block to help us to think about it. So first, we know there's a push force here. There's a friction force going up, gravitational force. going downward. And the normal force. So gravitational force is 0.5 times 10, which is 5 Newton. All right. So before I move on, I wish that you can pause the video and try out this problem by yourself. Now you have the free body diagram. How would you find the friction force in this case? And there are some misconceptions about friction force. And so I would definitely hope that you can just do it and try to compare your way and my way. And then hopefully that can clarify some of your misconception. All right. So the stories about friction force is always a little bit more complicated. Because now its definition, like the way how friction force work, it's already complicated because it's sort of different at different cases. In static, maximum static, or kinetic, they have like a different way to do it. So when you get a problem like this, how do you know which friction force formula to use? Or is this box moving, or is this box not moving? Like what's happening here? All right. So now let's see the physics together. If you look at this, and we know like here I will exert a force in this direction, and a normal force in that direction, and this box we know it's not moving in x direction at all. So these two forces, they should cancel out, which means if this is 15 Newton, the normal force must be 15 Newton as well. All right, and how about the friction? If these two forces, they are the same, like have the same magnitude, then they will cancel out, so this is not moving. But how do we know this object is moving or not moving? So to do that, we should always check. If the friction force is 5 Newton, then these two will cancel out. But if the friction force is less than 5 Newton, then it will just then this object will start dropping. So let's see, what's the maximum amount of friction force will happen here for this surface? The maximum friction force, static friction force, is mu s Fn. Mu s is 0.2. Normal force is 50. So this is 1. All right. So the maximum friction force is 1 Newton. Oh, sorry, it's 10 Newton. Okay. And so it seems like so this friction force, you can see for this friction force, it can go up to 10 Newtons. So if this is 5 Newtons, the friction force can be 5 Newtons as well, and they will just completely cancel out, and the block will stay imbalanced, will stay at rest. So the friction force here should be static friction, because the maximum friction is force is 10 Newtons, so you can see that I can definitely have a friction force like less than that. All right, so which means my static friction force should be equal to 5 Newton. So this I am using F net equals to MA, if you're not following here. And F net is F minus Fg, and it's not moving, so it's 0, so F equals to Fg equals to 5 Newton. All right, so this is where I get it from. All right, so if this is still somewhat confusing, let's look at another case. Let's see what happens if the mass is 1 kilogram. If the mass is 1 kilogram, which means the free body diagram in the y direction, the gravitational force would be 1 kilogram times g, which is 10 Newton. All right, so if this object is at rest, which means this friction force should be also 10 newtons to cancel this out, right? And which is okay because the maximum amount of friction force we can have on the wall is 10 newtons. So yes, it is possible. So in this case, the friction force would be 10 newtons. Again, I also get this from Newton's second law. Like the same logic. All right, so now if we look at the third case. What happens if this object is 2 kilograms? Then we can look at the free body diagram. Again, y direction will only have friction force and gravitational force. Gravitational force is mg, so that would be 2 times 10, that's 20 Newton. All right, so now my friction force, I have to provide 20 Newton friction force here to cancel this out so that it will stay at rest. But it's impossible because the friction that we just calculated, right? Like the maximum static friction force is only 10 newtons. So this friction, this guy can never provide more than 10 newtons. All right, so if it cannot provide more than 10 newtons, which means this force is always greater than the friction force, so this object will keep sliding down. When this object is sliding down, what is the friction force in this case? Is it still 10 newtons? It's not, right? It's because it started moving. So the friction force would be the kinetic friction, which is mu k times Fn, where mu k is 0.18, I believe. And the normal force is 50. So this would be 9 Newton. So the friction force will be 9 newtons in this case. All right, so I hope after this example you can understand what is static friction, what is kinetic friction, and how is maximum static friction can help you to understand whether this object is moving or not. So that's it. And again, in the dynamic part, we talk about the relation between F and A, F equals to ma. We also talk about all kind of forces and where they're coming from. And you can see based on where they're coming from, we may have some equations like definitions for these forces, which looks like this. So it's very important for you to understand what does this really mean, what's the meaning of each variables, and how to when this is applicable in what situation. All right, and when you feel like you're done with the definition, you can always try to use Newton's laws like F equals to ma or this guy, third law, to find out whatever unknowns that you need. And remember, force is a vector, so when you do F equals to ma, you need to do F equals to ma in x direction and F equals to ma in y direction. You cannot just randomly add up. For example, you cannot just add up these four forces together. That just doesn't make sense, right? It's not like it's 2, 3, 4, 5 Newton. The net force equals 2 plus 3 plus 4. No, it doesn't work this way. All right, it has direction, so we need to split up everything into x component and y component. All right, so I hope this is helpful, and good luck on the exam.